Okay, so welcome everyone to our data science and computational statistics seminar. It's my great pleasure to introduce our speaker today, Professor Lara Trussardi. So I will briefly introduce Lara. So Lara obtained a PhD in 2016 at the Technical University of Vienna. During the year 16 and 17, she worked as a postdoc researcher at the National Institute for Research and Digital Science and Technology in France. During the year 17 to 21, she was a researcher at the University of Vienna. And recently, she has become a junior professor at the University of Konstanz in Germany. So today, we will talk about two structures preserving time discretizations for gradient flow and application to generic system. We are very happy to have you here. So please, Lara.
Thank you very much for the introduction, and thanks also for the invitation to give this talk and the possibility to talk about my work in collaboration with Ulysses Stefanelli from the University of Vienna and Ansgar Jüngel from the Technical University in Vienna. So this was a work that has been done while my time in Vienna. And as you mentioned from my title, so what I want to do, the idea about this work was to find a special discretization for a gradient flow. And in the second part of my talk, I will talk about an application of this scheme to the generic system. So don't worry if you never heard about it. I will explain you what I mean. And of course, if you have any question or something it's not clear, you can also interrupt me anytime. If I don't see that you have a question, please, some of you just show up so that I will interrupt myself. So the starting point, as it was written in my title, are the gradient flows. So gradient flows have really a lot of applications which really cover several cases. Like I mentioned some of them here, like the heat equation, the Hell cell, the porous media, but really this is just a short list. I wanted to show that this kind of problem have really a huge variety of applications. And mathematically, they are written with this formula, which is a u prime plus a d phi equal to 0. So u is a trajectory and phi is a potential. So what's the idea of this expression? So imagine I want to make this kind of comparison, hoping that it will make things clear. So the idea is that you are, for example, on the top of a mountain and there is a very dense fog, so you don't see anything around you. And so the idea is that you are at a certain point, as here in my picture, as the point x0, and you check which is the direction with the steepest descent. So, and you start walking in that direction. After a while, you stop and you check if this direction is still the right one, or if you should adjust and go somewhere else in order to get the steeper slope, and then so on. So you hope that in a finite time, you will reach the bottom of the mountain or a hole, because of course, if we imagine that there will be a hole, this method could also bring you not really on the bottom of the mountain. But the idea of this gradient flow is that with a certain, so we have somehow to decide how often we adjust our step, because of course we cannot just stop at every step and check if we did the right direction, because we would also lose a lot of time and energies. On the other side, if we do it too rarely, what might happen is that we would have to do a lot of path for nothing, because we would go in the wrong direction for too much time. So usually these are the problems that arise when we want to consider a discretization of this gradient flow, and when we do a gradient flow at also the continuous level. So the point now is that this gradient flow structure, this gradient flow equation, can be written also as an energy equality. So solution to our gradient flow fulfill the energy equality that I wrote here. So the idea is that we have an energy drop. So phi ut minus phi us is an energy drop. This is equivalent to the integral between SF and t of our u prime square. So what's interesting here is that actually the other way around. So as you see, I wrote two arrows. So solution to the gradient flow fulfill the energy equality, but the other way around doesn't hold. So how can we somehow recover this second implication? So in this second equation, there is a u prime, and we said that u fulfill is a solution to the gradient flow. So we could split this u prime as a 1/2 u prime plus 1/2 u prime. This is a u prime. And then we replace one of these two terms, 1/2 u prime plus 1/2 u prime, with this term, the d phi. Because if we just rewrite this equation, we know that this term is equal to minus this term. So if we take the square of this term is equal to the square of this term. And so we get this second energy equality, where I just replace, so if this u prime by a 1/2 u prime plus a 1/2 u prime, and then here I replace the second 1/2 u prime with this d phi. So if we consider this second version of the energy equality, then we have that this an equivalence at the continuous level between the gradient flow and this equation. Okay, so how does it read? We have an equivalence between the gradient flow and the second energy equality. If we consider the first energy equality, then we have one implication that doesn't hold, so we couldn't come back. Okay, this is the setting at the continuous level. Now, I mentioned that I want to talk about structure preserving time discretization. So we want to do a numerical scheme. We want to write numerically this gradient flow equation. So the standard way when we want to discretize a gradient flow is to use the Euler method. So what we do when we do the discretization, for the gradient flow, we consider an Euler scheme where I replace this u prime by this finite difference, ui minus 1 over tau I, where tau is this time step. And actually, we can also write a discretization for our discrete energy equalities by replacing actually this u prime that we had with this finite difference. So as we have here in the Euler scheme. What we observe here at the discrete level is that we have now an equivalence between these two discrete energy equality. So we have an arrow that goes in both directions. The problem at the discrete level is that we lose the implication that we had at the continuous level. So solution for the Euler scheme do not fulfill any of the two discrete energy equality. So we lose this structure preserving that we had at the continuous level when we consider the Euler scheme. So that was our starting point. So this is a kind of motivation of our work. And so what I want to talk about today, I want to discuss about two schemes which recover the discrete energy equality. And the schemes I'm going to talk about are the so-called Gonzales scheme and De Giorgi scheme. So they have a name because actually these two schemes were already on the market. So we didn't really invent them, but what we did was to provide some theoretical analysis focusing on the solvability and convergence. So the scheme were already existing. And what I want to do now is that I would like to show, so I will show you how these two schemes work and how we, which are the properties that we get in order of existence and convergence. So let's start with the first scheme, the Gonzales scheme. And so we have our Euler equation, which was the discretization for the gradient flow. What we do for so Gonzales, what Gonzales did, not what we do, what he did was just to add this term here to the Euler scheme. So by adding, okay, this term, probably it looks quite, I mean, for you it's, okay, why, how do we get it? So I want just to observe that if we take the product between this scheme and ui minus ui minus 1, we get the discrete energy equality. By multiplying, we get a simplification, and we just get back to our discrete energy equality. So the point is that the Gonzales scheme, if we start from a point which is not already a minimum, so d phi is not, so ui is not equal to ui minus 1, what we have is that the scheme satisfies the discrete energy equality, so the scheme is stable. So that's the first point. But of course, written as it is, it looks not really clear. Okay, if I multiply by this difference, then I recover the discrete energy equality, but maybe it doesn't really, it's not really immediately the meaning of this scheme. So I will just rewrite this Gonzales scheme in another way. So these two versions are completely equivalent, but if we consider the box on the bottom, so we see what the Gonzales scheme does. So this Gonzales scheme is a system of two nonlinear equations. The first one is the discrete energy equality, and the second one is a parallel condition. So we want that ui minus 1 is parallel to d phi. So this, now it's clear how we recovered the property that we wanted to have at the discrete level, why it holds. It's just written into the scheme, but we also have to add this second equation. And as I mentioned now, we're going to see which are the nice properties. Yes, I think there is a question from Giovanni.
Yeah, thank you, Lara. I got like some kind of trouble. Probably it's just my problem. I got puzzled with the notation.
Yes.
So we assume that U is a vector, I presume, because otherwise the norm will become an absolute value. Is that correct?
Yeah, U. So in this case, yeah, you could be a vector. Yes. Okay.
Yes.
It depends on which dimension you're working. Yeah.
Yeah. I mean, okay, let's say, so this can be easily extended to a vector problem, which will make totally sense, the L2 norm. And second, what is tau? I think it's the time step, right?
It's a time step, yes, yes, sorry. Yeah,
right. Yeah. And the boundary condition?
So here I'm not talking...
sorry, initial condition, my bad. Initial condition.
Initial condition. Yeah, we give a u. Let's say it's given the ui minus 1.
Okay, thanks.
Yeah, sorry. Yeah. Thank you. Of course.
Welcome. Thank you.
Yeah, of course. As Giovanni highlighted, of course, we have an initial condition. So ui minus 1 is given, and then we want to build the solution ui, where tau I is the time step. Thank you. So what I wanted to say now is. So I told you that what we provide was some existent and convergent result. And I put here like a sketch of the proof just because I think that just showing you this, you will see which are somehow some troubles that we could get using this method. So when we want to prove the existence, the idea we had was the following. So we consider a compact set K, which was given actually, as you see, by the discrete energy equality. So the set of the U which fulfill the discrete energy equality. Yes. There is another question. No? Okay, I continue if there is a question, just interrupt me. And then, okay, we observe first of all that K is not empty, because if we take as U, ui minus 1, then we see that ui minus 1 is in K. And secondly, we want to maximize the function. So ui maximize the function that goes from U to U minus ui minus 1 square. And if you are not already in the minimum point, then K, it's not just the element ui minus 1, so we could get a ui different from ui minus 1. So why I wanted to just sketch you these 3 steps, because the fact that K is compact reduce this method to a finite dimensional space. So the point is that we were looking for a proof that would just not have this restriction, but we were not able to somehow to find one. this doesn't mean that maybe someone of you would have an idea how to solve this problem, but due to the fact that we are obliged to have a K which is a compact sublevels, it means that this is the Gonzales scheme admits solution for sufficiently smooth function phi and finite dimensional space. What about the convergence of the method? So here, for simplicity, I just took this version of the scheme, because here you can see that then we can just write this term equal to this other part, because it's the sum is equal to 0. And then we can just write that this term is smaller or equal than a term which we have this tau I. So where tau I was so the time step. So, okay, Giovanni has another question, I think.
Yeah, sorry, I don't mean to bore.
Yeah, it's fine.
I'm just asking question because I think it's interesting. So,
yeah, it's perfectly fine.
So it's the other way around. So practically, I'm getting a bit confused. You're saying essentially that the upper bound of this inequality depends on tau, which is the time step at step I. But I don't think it's true, because actually we have an L2 norm, which will become times tau. I believe it's always positive. We can assume that tau is always positive. So the tau, the 2 tau just goes, oh yeah, oh sorry, I missed one step. Oh, that was totally worthless. That was a total worthless interruption. Sorry, okay. I missed the equality over there.
That's perfect. That's perfectly fine. If you understand the point, then
sorry.
It's perfect.
Cool. Okay, I self-answered the question. Thank you. Anyway.
Perfect. Cool. No, here I just wanted then to mention that we have a convergence here with actually an explicit and sharp a priori rate, and for the Gonzales scheme. So if we want somehow to say what we have for the Gonzales scheme, is that this is a stable scheme. We have existent for sufficiently smooth function, and also a convergence for also some class of potential. Which are the, let's say, the shortcomings for this method? So you already understood from what I told you before. So this analysis is just valid for smooth function with compact sublevels. That means that we are essentially restricted to finite dimension. Moreover, if we implement numerically this scheme, usually the idea is that we implement the second version. So we have two equations, the balance equation and the alignment condition. So at each time step, we have to solve a nonlinear system. And then we have a condition on the time step when we are in a non-smooth case. And the last but not least, this probably can't be written as in a variational form. So this is what we have now for the Gonzales scheme. So you have an overview how it works, which are somehow the things that work and the minus side of the scheme. And now I want to talk about the De Giorgi scheme. So, sorry. The De Giorgi scheme, actually, it's the second energy equality I show you. I don't know, maybe you don't remember how it was formulated, but here we just have this, what was the U prime, so our 1/2 of this finite difference, and then we have the 1/2 of d phi, our potential. And when we consider the De Giorgi scheme, actually we could consider two options, let's say, the two cases. The case where we study this g equal to 0, and the case where we want to minimize g. So when we want to minimize g, it means that we allow a residual that I call here alpha I. So we would allow to have some, we would allow then this term to be there. Why do I consider these two different options? Because actually we get two different cases depending on the choice that we have for the residual or not. So if we take a potential which is convex, we have existence for the case where we study g equal to 0, so without residual. And if we allow the residual to be of the order of tau square, where tau is the time step, then we could prove existence also for potential which are smooth. And then we could prove convergence if the sum of the positive part of the residual is going to 0. So this means that we have, if we consider the model without residual, we could show the convergence, and we could also show the convergence for the problem with the minimization. And I just want to show you this second case. It's also, the slide could looks quite ugly, but I'm going to read it with you so that you understand what I mean. So we said that we wanted the sum of the positive part of the residual goes to 0. So the limit is equal to 0. And then our De Giorgi scheme was written as this term plus alpha I. So I can just write that this limit is greater or equal than limit of what we had for the De Giorgi scheme. And now we can somehow pass from the discrete to the continuous. So we just replace this sum by the integral. And then these are just some easy calculation. We put this phi of ut minus phi of u0 inside the integral. This is just a series of equality. And what we get here is that actually is u prime plus d phi is equal to 0. So if the sum of the positive part of the residual is equal to 0, then u is a solution to our gradient flow. So we have the convergence to our solution u as we want. So the De Giorgi scheme, for the De Giorgi scheme, we have existence and convergence, even if non-smooth and infinite dimensional situation. And we have a sharp error estimate for finite dimensional case. Moreover, if we consider the problem with the minimum, so not the Giorgi equal to 0, but the minimum of the functional, then we even have an optimal error bound. And the last nice property of this De Giorgi scheme is that it can be extended to a nonlinear evolution setting. So here we were talking about gradient flow, and we could write a De Giorgi scheme for the gradient flow, but this could be applied to generalized gradient flow, to the curves of maximal slope, and these famous generic flows I mentioned in my title. So I just mentioned what's the meaning of this generic. So generic means general equation for non-equilibrium reversible irreversible coupling. So it looks it's a very long title, and it's just a way to rewrite a problem. And I will show you in a couple of slides how we define this generic. But I wanted to mention that this is a formulation that had been introduced in 1997 by Grmela and Oettinger, and we could just rewrite then our De Giorgi scheme. So for this setting, so here we have some special structure that we just keep. We have this psi that comes into the game, and I show you how then we get all these ingredients. But I just wanted to tell you that the De Giorgi scheme could be applied to this much more generical non-linear evolutional setting. But before talking about generic, I want to mention a couple of things. So first of all is that the Gonzales scheme falls into the class of discrete gradient methods. That means that you have an exact reproduction of the dissipative dynamics. We were thinking about some higher order scheme, but the problem is that they do not really replicate the exact energy dissipation for dynamics for the gradient flow problem. And that's the same when we were looking if there was a possible generalization, a higher order generalization for the two scheme I talk about, like something like Runge-Kutta, but the problem is still the same. So there's no replication for the dissipative dynamics. And just to mention, if some of you know them, we have a connection with the optimization, like with the proximal algorithm. And before talking about generic, I also want to show you a comparison between Gonzales and De Giorgi, because of course I talk about one, I talk about the other one, what's the one compared to the other one. So I just take a very simple ODE, u prime minus lambda u equal to 0 with initial data equal to 1. So this ODE can be seen as a gradient flow with this potential phi of u of lambda u square over 2. Lambda is positive, and I think I'm going to take it equal to 1 for simplicity in the simulation I'm going to show you. And then we consider 4 different solutions. So the solution of the Euler scheme, the Gonzales scheme, and the two solutions for the De Giorgi scheme, the one equal to 0 and the one with the minimum. So in this case, the problem is really easy, so we can even write explicitly the 4 solution that I just wrote here. And now, so the first simulation is the performance of the method in terms of the order of convergence. So lambda is equal to 1. And so this solid line, for example, is the difference between the exact solution and the Euler solution. On the bottom, actually, we have the difference between the exact solution and the minimum De Giorgi. So we see that Euler and the minimum of De Giorgi have the same order of convergence, which is the order of tau. On the bottom, we have the difference between the exact solution and the Gonzales. So now you tell me, okay, but this is better. Yes, this is the order of convergence tau square. And I forgot to mention that in one dimension, actually the order of convergence for Gonzales is 2. But it's just working because it's a very simple ODE, it's 1D and everything is nice. While if we take the De Giorgi scheme equal to 0, this is the line on the top. This is this has order of convergence 1/2. And sorry, this is tau square and 1/2 tau, of course. So what we are interested in now is to perform in order to compute the performance in order to compute the minimum of our potential. So what we do here is we check what's the reduction of the potential along interaction. So here we have tau lambda equal to 1/2, yeah, and here we have tau lambda equal to 5. So what's happening here? So let's just focus, for example, to this dash dot line, which is the line corresponding to the minimum for De Giorgi. We really see that here we have a different behavior. So for tau lambda getting bigger, it seems that we have a better performance. So this was the reduction of the potential along interaction. And what we thought was like, okay, what's then the effect of this tau lambda? And so here we fix the number of iteration, and we plot the reduction of the potential as a function of tau lambda. So what do we observe? So let's start from this dot line. So this dot line is the Gonzales scheme. So, okay, we have this kind of singularity here, and we observe that this Gonzales scheme actually has a strong energy reduction for tau lambda smaller than 2, but then it's really bad. It has no strong energy reduction at all for large tau lambda. The straight line is the Euler scheme. And these two lines are the two De Giorgi. So the De Giorgi with the equal to 0, which also has a singularity at 1, and the De Giorgi with the minimum. So the feeling is that this De Giorgi with the minimum has a very strong energy reduction for large tau lambda. So these were some simulations for comparing the Gonzales and the De Giorgi scheme. And now I would like to pass to the second half of my talk, where I tell you what's this generic formulation. So the generic formulation in the beginning was applied to some thermomechanics and electromagnetism problem, but you could really find papers where this formulation is written for several kind of problem, which are like shape memory alloys or so Boltzmann equation. And the idea of this formulation is the following. So we write our problem in this way, where Y is a state of a closed system, E is the total energy, S is the entropy of the system you're considering, and then L and K are two matrices which have some special properties. For example, L has to be antisymmetric, K has to be positive, definite, and moreover, these L and K have to satisfy this non-interaction condition. So if we take L star ds, this is equal to 0 as K star de. So this is really looks really abstract, But the idea of this generic formulation by Grimela and Huttinger, it's that you could write somehow any problem with this structure. You define the state of your system, you write the energy, you write the entropy, and then you can just write. Yes, Giovanni.
Yeah, it's becoming a bit bothering, my presence. Actually, I was wondering what's the difference between L and L star and K and K star.
So it's when you have the when you write the, so how do you call it? Well, I lost the term.
No worries.
Wait, how is it called? It's the
Dual.
Yes.
The dual operator.
Yes, exactly.
Okay,
sorry,
cool.
I was looking for the word. Thank you very much.
No worries. Thank you.
So they have this special non-interaction condition, and you just write in this way. So which are the nice property? Because then now you might wonder, why are we interested in writing our problem with this formulation? So the idea is that we have the conservative and dissipative dynamics, which are separated, writing the problem in this way. We have the conservation of the energy and the accumulation of the entropy. So here I just wrote this series of equality just to show you quickly why we have this conservation of the energy. And this really comes out from how we define this L and this K. So we really had these non-interaction properties that will really allow us then to just get that this energy is conserved and the entropy is accumulated. So the question now is, okay, this is an abstract formulation. How can I recover and replicate these properties at the discrete level? Because of course, then we were still wondering how we could do a discretization for this system. So there are numerical schemes that conserve energy, which are called the discrete gradients method. And these are somehow gradients of functional, and they are specifically modified in order to fulfill a special discrete chain rule. And they also have exactly replication of the exact replicate conservation. When we talk about some thermodynamical mechanical context, then there have been obtained some structure preserving discretization in terms, for example, of the absolute temperature or the internal energy or entropy. And then there is also some numerical scheme which conserve energy and accumulate the energy. And these are called generic integrators. But the problem here is that we have to modify the energy and the K, the matrix, so this operator, in order to have this energy conservation. So we have somehow to really change a bit things in a proper way. So what we suggested for this generic formulation was to use a minimize movement scheme. So at all discrete steps, we want to solve a specific minimization problem. So somehow now you remember when I told about this De Giorgi scheme, where we were minimizing the functional. So before doing this, we need to define the entropy production potential. So we have our K that is given usually when we write the system, and we have to just introduce this psi written in this way. So it's just a lot of calculation. And then we rewrite our De Giorgi scheme in the following way. So if you remember here, we have the phi of US minus phi of U0. So this is replaced by the entropy. And then these two other integral, which were the U prime and the d phi, are replaced by this psi and psi star. So with this entropy production potential. And then these are somehow the terms that we had in the generic formulation. So this is at the continuous level. And then as before, we can just write what we have at the discrete version, where we replace this y prime with this finite difference. Okay, so what's now the scheme we want to apply? We want to solve a minimization problem where G is defined as follow. So this formula looks really abstract. It's not probably maybe clear how we can apply, okay, what's psi, what S, what's this L. So I'm going to show you a very concrete example now where we want to apply this minimizing movement scheme. So we consider the damped harmonic oscillator that you probably have already heard about. So we have a system with these two equations where Q is the position of our harmonic oscillator, theta is the absolute temperature, and then we have several constants, m, nu, k, lambda, c, which represent all the constants we have in this oscillator, like the mass, the viscosity, the elastic modulus, and so on. So this system can be rewritten as a system with three ODEs, Q prime, P prime, theta prime, where P is the momentum. So defining P as the momentum, this system can just be rewritten in this way. Okay, and now I show you that we can write this problem with using the generic formulation. So how do we proceed? So I just recall you what was this generic formulation. So the first thing we want to define is the status, this Y. So we say that Y is the tripole Q, P, and theta, okay? And then we have to define the energy of our system and the entropy. So these are given from the oscillator, the energy and the entropy. Then of course, from the energy, we can compute what's dE. From the entropy, we can compute what's ds. And then we have to define what are our L and K. Remembering that L has to be antisymmetric. So as you see here, K has to be positive, definite, and symmetric. So as you see here. And then what we have, so trust me, or if you want, just copy the matrix, copy the entropy, and try to do your own computation. If we just plug in this L, this K, the dE, and ds, actually, you can write this generic formulation, but this generic formulation is just this system I wrote you before. So this system is absolutely equivalent to this formulation, taking this E, this S, this L, and this K. So if you want, it's just a much more complicated way to write your system. But here we have this nice property. So we have these dissipation and conservation properties which are separated. We know that the energy is conserved and the entropy is increasing. Okay, so we wrote our problem with the oscillator with a generic formulation. And now we want to apply our minimizing movement scheme. So what we have to do, first of all, we have to write this entropy production potential, psi. Sorry. And this psi, actually, we had a formula to write it. Now we know what's K, because I wrote you in the previous slide what was K. So we just replace, and we get the formulation for psi, a formulation for psi star. And then we just have to plug in this very probably horrible formula that I show you in some slides before. And we just get a nice, if you want, expression. So here it's our incremental minimization problem. So we want to find a minimum on Qi, Pi, theta I for this expression. And here we have some constraints that arise when we write this minimization problem, but they are physically they have a physically meaningful, like the temperature has to be positive. For example, this is a constraint that we have in our, as a constraint that we have for our problem. Okay, so this is our minimization problem. And of course, let's see which are some properties that some properties. So first of all is that the energy is conserved. So for each time step, the energy is constant. We have a bounds on the sum of the absolute value of our variables. So the sum of the Pi plus Ti plus Qi is bounded. And we can show that there is a minimal temperature. And so it doesn't matter which kind of time partition we get, but we always have that at all time step, this theta I is greater or equal than this theta mean. And now the question is, okay, you wrote a nice minimization problem. How can you be sure that there is a minimum? So what we do now what I want to do now is to show you that we can really have a minimum for our minimization problem for this oscillator. So I fix a y bar where a y bar is just a given threshold. So we know at the time step I-1, q, p, and theta. And now we want to consider the function that associates to y, our minimization, our g, tau I, y bar, y. So this function is smooth. So we have to check the coercivity. That means we have to check the sublevels of this function are bounded. So what we do is just rewrite qi and theta I as a function of pi. So we just replace what we knew. So we knew an expression for qi, pi, and theta I. We replace everything in p. And so the idea now is that instead of having a minimization problem on qi, pi, and theta I, we could just get a minimization problem on pi for a new f, where now f is just an expression of pi. The point is that, so I didn't write the full expression because it was a very long, disgusting formula, and that's mean it doesn't make sense now. So theta I want just to say that theta I is an expression as a second order function of pi. So the constraint here is that we want the temperature to be positive. So this is what we have to take into account. And the minimization problem, it's just on the variable pi now. So instead of checking if the sublevels are bounded for now for g, we have to check it for f. And this holds for because capital F of pi goes to infinity if small f of pi goes to 0 plus. So the only thing that it's left to be proved is that this f to pi, that was the theta I, is positive on bounded interval. And this interval might depend on the data that we have and if the time step is small enough. So this f was a alpha pi square plus beta pi plus gamma. So we want alpha, the coefficient alpha, to be negative and the coefficient gamma to be positive. So here you probably see why I didn't write the full expression, because that was gamma. So it's quite horrible and it doesn't make too much sense. But what I wanted to say is that alpha is negative if tau squared is smaller than 4m over k, and then gamma is positive if tau is smaller than this value. So if we just fix, for example, all the constants equal to 1, we observe that tau squared has to be smaller than 4, and tau I has to be smaller than 2 theta min. So if tau, that was the time step, is small enough, then we have the existence of a minimizer. Okay, so let's see some simulations so that you probably understand how this minimization problem works. So I just take, as I mentioned, all the constants equal to 1 for simplicity, initial data in 1, 1, 1, final time 15, and the time step 1/4. So it's quite big if you take 1/4 as a time step. So here is the position, the momentum, and the temperature with respect to time for the numerical reference solution and the minimizing movement scheme. So you probably even don't realize that there are 2 lines through except of here. So the red one and the dot one is the reference solution, while the black continuous one is our minimizing movement scheme. So we see that even with the time step, which is quite big, our minimization movement scheme works quite well. And the second thing we're interested is we wanted to check was if the energy is conserved, and that's absolutely the case, and if the entropy is increasing. So here you also see that there is a slight difference here between the reference solution and the minimizing movement scheme, but we have the properties that we wanted, the conservation and the dissipation. And the last picture I'm going to show you is the error. So this is for the momentum. We get exactly the same picture for the position and the temperature. That's why I just show you just one. And here we see that this is the order of convergence 1, and this is exactly what we get with our scheme. So our minimization movement scheme works quite well also for this kind of problem. And here what I implemented was really this minimization problem I wrote. That was this expression for qi, pi, theta I. I really wrote this problem with the constraint and run the code. And this is what we got. So for concluding, what I talk about today was these two different schemes, Gonzales and De Giorgi, which have exact dissipation, which replicate exact dissipation dynamics. For the Gonzales scheme, we have seen that this is well suited for smooth finite dimensional energies, while the De Giorgi scheme works also for smooth perturbation of convex energy in infinite dimension and can be extended to much more general evolution setting as the generic one that I show you in the second part of my talk. So thanks to all of you for your attention. And here there are the two papers where you can find all the details and the results I talk about today.
Thank you very much for the very interesting talk. So we have time for question. So if you have any question, just simply unmute yourself and ask Lara, please.
Can I ask a question? Lara, very interesting talk. I have a very general question, which is for Hamiltonian dynamics, we have some perfectly energy conserving schemes, but we also have the symplectic schemes, which not preserve the energy perfectly well, but it's kind of oscillate around true energy, but works quite well for long time simulations. Are you aware of this kind of scheme?
Not really. I mean,
okay. So my question really is for dissipative system where we kind of have a combination of Hamiltonian system plus some dissipations. What's your view of, or do we need to kind of preserve the energy perfectly, or we can kind of relax this kind of requirement? For example, if the energy is kind of fluctuating around its true value.
I think I saw a paper. I think it was from Milke, but now I'm not 100% sure. Probably I should check, and I can check, and then we can keep in touch eventually by email, where there was this energy that was not really conserved 100%, but there were some properties anyhow of the energy.
And so my question really is, what's your view of if we have some scheme which does not preserve energy perfectly, but what if it can preserve the entropy production very well, for example? Are you kind of happy with those kind of situation, or you are very keen to preserve the energy perfectly?
So no, here it was really, so in this setting, we really want to preserve the energy. That was really somehow a must, something that we really wanted to observe and we wanted to have. So because that was somehow our goal now, to really see if we could really preserve these properties. So in this setting was really a must somehow.
Okay,
and
thank
so
you.
That's why also we didn't care about something, other option.
Any other question, please? So may I have a question? Here you consider for what is the harmonic oscillator, right? Is there any chance to extend to non-harmonic oscillator? I mean, when the external potential is not quadratic.
I think so. So the trick here somehow is to be able to write this generic formulation, because even once you set what's your state variable, the energy and the entropy, no one is giving you the K and the L. So it's your job to find the right K and the right L. And sometimes you think it's easy, and it's much more complicated than what you think.
No, I mean, in terms of the discrete scheme, so for harmonic oscillator, you can, for this system, you can often approve of conversion, right? Yeah, so for the De Giorgi scheme, it's also non-convex situation. It's also working. Yeah, non-smooth. Yeah, I think it's okay. It's so I think we just work now with convex function. So with convex function, for sure it's working. If it's not convex, you have to be careful. You should take some perturbation. So you should split probably the convex and the non-convex part, but I think it's also valid, if I remember correctly. And as you said that there is some condition on the time step, but you can take it quite big.
No, yeah, so the condition, we had a condition on the time step, especially, but yeah, I mean, so yes, you have a condition on the time step, but it's quite general. So in the end, in the special framework, we were really allowed to take also a big one. If you would choose another problem or whatever, you would see that means some or other choice for your potential, you would really need a small time step.
I see.
And if the time step is too big, then things are not so well simulated. Simulation is not so good.
Thanks.
You're welcome.
Actually, I was wondering if I may allow to ask a question. What happened with some input noise? Like, for example, a delta as an input, like a sudden input. How would it behave?
That's a good question. Yeah, I should check my simulation. You're right. Would be interesting. So I think,
or maybe like with an indicator variable, also called I forgot how it's called in English. So in math, you know, it's just a time. I don't remember.
The Heaviside function.
Right, Heaviside function. Yeah, I call indicator function because of my background.
I know. We understand it.
Yeah, the Heaviside function. Because anyway, it's smooth. But like, yeah, that's another concept. When you were talking about, like, okay, let me make clear one part. When you were talking about smoothness of a function, you know, we all know smoothness is a very fuzzy concept. What do you exactly mean for smoothness?
Yeah, that you want to have some special property, should be C2, C.
Yeah, exactly. Yeah. How many derivatives would you like for?
I think the existent was C1. For this convergence was a C2, I think.
Oh, then would be interesting to see an Heaviside function, because anyway, if I don't remember wrong, C1 is for sure. C2, I think, should be 0.
Yeah.
Then,
but what do you mean to take as initial?
Like an input and the output. So practically, you have a period where there is an Heaviside function that is turned on. So you have like kind of rectangle.
Yeah, kind of jump. Yeah,
and after you shut down by another input of an Heaviside function with with the opposite sign. And this should be anyway smooth, because they are both derivable at least once. And that would be.
Yeah, that would be interesting to see what happens.
Like the different schemes, how they would approximate. Because I have some, like, I got this problem when I was doing a model. Like, okay, you know, I was doing some Kunja-Root. I was like, okay, this is a really interesting part when I have to implement an impulse to the model. And I saw that I really needed to make sure that in the time step the impulse was included, because otherwise the scheme wasn't able to detect. So that could be like quite an interesting.
Yeah, absolutely. Thank you for the hint.
No, that's all right. But thanks.
Can I ask a follow-up question from Holmes' question? So for example, because you showed for the minimization scheme for the harmonic oscillator, it has some nice property like you can show that's unique and it existed. And my question is, and does this minimizing scheme still have those nice properties for general nonlinear potentials rather than harmonic oscillator?
Yeah.
Or sometimes some of the term can be quite, tedious.
So I think that for this minimization, so if I remember correctly, when we did this minimization movement scheme, we really applied to this special case because we wanted really to show what happens in a very concrete case. I think we did also a bit more general framework in the introduction of the paper, which is this second one. And so also there you have some restriction as the generic one, but now I don't remember exactly. But you always need some kind of smoothness condition, or like C1, C2, or also for this minimization movements approach. Yeah.
Okay, thanks. Yeah, thank you.
But it could be non-smooth, I think. I mean, there are some cases where if the potential is not smooth, could also work. You just, I think in the proof, we just split our potential as a sum of two functions with some properties, and then it was working also in non-smooth case.